Today we're going to talk about numerical optimization. So in the previous chapters, we talked a lot about optimizations without explaining how it works. So when we have an objective functions, then we talked about optimizations. So based on optimization, we can find a solution like that. So now in this chapter, we're going to talk about how optimization algorithms work and what kind of algorithms we have and what is the difference and what is the principle, etc. Okay, so basically we'll talk about optimizations. What is optimization? And then there are a couple of algorithms. So these algorithms can be categorized into one of the three methods. So first one is gradient descent method, and second one is Newton method, and the third one is trust ridge method. And they are all connected, but they have different features. And then I will talk about a little more advanced topics in optimization. First, people optimize. People optimize and so does nature. So nature optimizes. Or, if you will, nature is optimized. Okay. So everybody does optimization in our daily lives. Okay. And then optimization is an important tool in decision science or deep learning or in our daily lives. And we have some objective. Okay. And then this objective function is a quantitative measure of the performance, something like a profit or time or potential energy. So do you want to optimize something in terms of profit? Okay, then you can follow that direction. Or sometimes when we develop some system, then the time is the crucial factor. So then we can minimize the consuming time there. So we can come up with a very different objective function. So the objective can be represented by a single number or scalar. In our lives, usually we have many different types of objective values. Okay, sometimes we want to maximize our profit, and at the same time, we want to increase our happiness, or we put lots of emphasis on the relationship with our family members or friends. So we have many different values, right? So it is all about the value systems. So it is really complicated to optimize our lives, but fortunately, in the system, in the deep learning or in the machine learning, we can come up with one single number as an objective function. It could be a loss function. And the objective depends on certain characteristics of the system. And these characteristics can be described by variables or unknowns, parameters. Often the variables are restricted or constrained. In that case, we can have a regularizer, which is a topic of the next chapter, regularization. Here is an objective function, and we have variables. Think about the neural network. So we have lots of parameters, and then with these parameters, we can classify or we can estimate some value. Then on top of this neural network, then we can define the objective function like mean squared error or cross entropy. Okay, so cross entropy is objective function in that case, and then the parameters of the neural network would describe the characteristic of the system, and then by controlling these parameters, then we can minimize this cross entropy. Then in this chapter, the question is how? How can we control these parameters to minimize this objective function? That's the topic of this chapter. Okay, so here's our goal. Okay, so after problem definition, which means after identifying the objective function and variables and constraints for a given problem, for example, when we have a neural network, then we define the neural network architecture. So we can define the parameters in the neural network. And then we can define the objective function like cross entropy or mean square error and so on. So now, okay, so everything is formulated and defined. And then our goal is to find the values of the variables that optimize the objective function. Okay, this is what we want. And optimization algorithm can be used to find its solution, obviously. And for many problems, it is hard to select the best solution directly. By this, I mean sometimes we can come up with the analytical solution. So mathematically, we can prove the equations. We can find the best parameter from the equation. But for many problems, it's not easy to find an analytical solution. So in that case, we can update the parameters iteratively, and then we can converge to the optimal value gradually. So in this chapter, we are interested in that kind of problems. So we cannot find the best solution with one equation. We have to update the parameter many times. So we are going to see lots of algorithms, but unfortunately, there is no universal optimization algorithm. So we are going to talk about many different algorithms, but we don't know which one is the best. So I recommend students to try these optimizers for your problem, and you have to find which one is the best optimizer for your problem. Okay, sometimes SGD is the best, sometimes Adam, sometimes RMS prop, we don't know. You have to try many optimizers at the beginning of your experiments. Okay, and then once you know which optimizer is better than the others for your problem, you can use that optimizer to train your networks in your experiments. Okay, then why do we talk about optimization? As I said, the training process is all about optimization. So we have to talk about optimization. Okay, so here's a joke which is not funny, but in machine learning or deep learning, people say every problem is just optimization problem. So when we design our neural network and the objective function, okay, so everyone can do that. But the problem is optimization is not that easy. Okay, you have to try many different configurations and you have to come up with a better idea to figure out what kind of configuration is the best and so on. So optimization is a crucial part in the deep learning or machine learning. Okay, so training a model is an optimization process. So training is to optimize an objective function f with respect to the parameters w. W is a vector. I know in neural network we have some matrices and the vectors, but we can vectorize all the parameters. So we have many matrices and vectors, but anyway, we can put all these parameters into one single vector. So let's assume that we have one vector w as a parameter. Okay, and then the objective function is defined on top of a model, as I said. If we have a neural network, then the objective function is defined on top of the neural network with the label and the output of the neural network. You know, we want to minimize the difference between the label and the output of the neural network. That's what we want. And without loss of generality, we're going to consider minimization problems. If you really want, you can drive all the equations, everything based on the maximization. But there is no difference between the minimization and maximization, because if you put the negative sign in front of maximization, then it is minimization problem. Okay, so from now on, everything is minimization problem unless told otherwise. Okay. Sometimes we don't have a constraint, so we have one single objective function, so we're going to minimize this function without any constraint. But many times we will have some constraint like this. So we want to minimize this function within some area, or W should have some specific characteristics. For example, something like norm should be 1 or less than 1 or so. And in this graph, we have a objective function like this. Okay, this is our objective function, and this is the best place where the objective function has a minimum value. Okay, but now currently we are here. So from this point, we have to follow this. Then we want to converge to this place. Okay, that's our goal. But then the question is how? This graph summarizes 3 different methods. First one is based on the gradient. Gradient is simple. It just take the gradient of this function and then follow that direction. It's kind of greedy method. The second one is based on the quadratic model. So from this one, we actually approximate this objective function with the quadratic equation, and then optimize the quadratic approximation, and then follow that direction, and we will be here. And the third method is actually compromise between these two, gradient and the Newton method. So instead of taking this gradient, simple direction, or the quadratic method, then the trust rhythm method finds somewhere between these two. Okay, so we're going to talk about these algorithms later, but in this slide, what I want to talk about is there are three different approaches: gradient based method, and the quadratic model based method, and the trust rhythm method. Before talking about some specific optimizers, let's talk about some characteristics of optimization solutions. Okay, first of all, there are two types of solutions. First one is a local minimizer, and second is global minimizer. And local minimizer can be defined by this. So let's say the W star is a local minimizer, then the value of this objective function is lower than the other function values in the local area. So as long as the W is close to W star, then the f of W star is always smaller than or equal to f of W. So in this figure, this is a local minima, and this one is also local minima. If we focus on this local area, then if we change this W in this way, then f of this is smaller than f of the other parameters. So actually we have to talk about the parameter on this axis. So this one is W star. F of F star is this one. Okay, this value is f of W star. This one is W. Then f of W is higher than f of W star. Okay, we focus on the local area. Okay, then global minimizer doesn't have any constraint like this one. Okay, so f of W star is smaller than or equal to f of W for all W. So this one is a global minimum. Okay, and this one and this one are local minimums. But in theory, it's not easy to find a global minimum because this function is endless. Okay, and then we have no idea what's happening somewhere around here. Maybe, who knows, this could go down here. So it's not possible. Also, when we are around here, okay, let's say we are at the local minimum. So we can look at the neighbors, okay? And then as long as my position is smaller than the other neighbors, then I can say this place is the local minimum. Okay, but beyond this hill, what's happening? We have no idea. So usually it's not possible to find the global minimum. So you don't have to be obsessive with the global minimization. Usually local minimization is good enough most of the time. And deep learning, we're interested in local minimum because global minimum is not possible. And the local minimum is good enough. And any local minimizer of a convex is the global minimizer, because if it is the convex, something like this, then there is only one minimizer, which is global minimizer. So in convex functions, the local minimizer is the global minimizer. Okay, but in general, as I said, global minimizers are difficult to find, so a local minimum is good enough. In deep learning, we are interested in finding good local minimizations. That's enough.